Welcome to the Module 9 notes. In this section, we are going to continue looking at the probability of events. This video will also contain the little bit that we need to know from Module 10, which is conditional probability. So the first thing we're going to talk about is the complement of an event. So the complement of an event is the probability that the event does not happen. So the first thing we have is the probability of the event and the probability of the complement of that event always add up to 1. Okay, so we can see just down here below here, we have the probability of an event, we're going to call that A, and the probability of A complement, or the probability that A does not happen, is equal to 1. So we can use this to find the probability of A. If I want to know the probability of A, and I know the probability that A does not happen, I can find the probability of A by taking 1 minus the probability of A complement. Same thing on the other side. If I know the probability that A is going to happen, and I want to know the probability of A complement, or the probability that A does not happen, I simply take 1 minus the probability that A does happen. So an example we have of this, I say if there is a 25% probability of snow tomorrow, what is the probability that it is not going to snow? So here A is equal to the event that it snows. And the probability of A is 0.25, turning that percentage into a decimal, because remember, percentage or probabilities have to be between 0 and 1. So we can turn a percentage into a decimal by dividing it by 100, or moving the decimal point 2 places to the left. So now I want to know what's the probability that it does not snow. So the probability of no snow is what? Well, that's the same thing as saying the probability of A complement, which would be 1 minus the probability of A. So 1 minus 0.25, which is 0.75, or 75%. So if there's a 25% probability of snow tomorrow, then there is a 75% probability of no snow tomorrow. All right, so moving forward, we're going to look at the union of two events. So the union is basically like the combination of the two events. We're going to start with disjoint events. So two events are disjoint if they cannot occur at the same time. You can also use the term mutually exclusive when talking about disjoint events. So if you have two disjoint events, the probability of the two of them occurring, either one of them, so we have the event A and the event B, the probability that the event A or the event B occurs is equal to the probability that A occurs plus the probability that B occurs. And notice that word or is bold. That is a big hint to tell you that you're going to need to do addition. So let's look at an example. Okay. Find the probability of the following events. So the first one is the probability that you roll a 1 or a 2 on a single 6-sided fair die. So it's not possible to roll a 1 and a 2 at the same time, which means they're disjoint. So with this, I'm going to do the probability of a 1 or a 2. It's going to be equal to the probability of a 1 or the probability of a 2. The probability that I roll a 1 is 1 over 6. So there's 1 on the die and 6 total numbers, plus 1 over 6, which gives me 2 over 6, and I'm running out of room. I ran out of room. And then again, remember, we always want to turn these into decimals, so 2 over 6 is equal to 0.3333. All right, now before I do the next example, if you are not familiar with a deck of cards, I recommend you pause now, go look up a picture that will show you all of the cards that are in a deck of cards, and then resume the video. Most of the examples for the rest of these notes are going to involve a deck of cards. So if you don't know what's in a deck of cards, go and Google it real quick and then come back to this video. So now for this one, I want to know what's the probability that I draw a king or a queen from a deck of cards. So we're looking at the probability. I'm going to start this way over here now. Probability of a king or a queen. Okay, so first I need to know what's the probability that I get a king, and I'm going to add to that the probability that I get a queen. Well, the probability that I get a king, there are 4 kings in a deck of cards, and there are 52 cards total, plus there are 4 queens and 52 cards total, so that gives us 8 out of 52, which as a decimal is 0.1538. So these are 2 examples of mutually exclusive or disjoint events and how to calculate those probabilities. Now, most things in life are not disjoint or not mutually exclusive. A lot of things in life can happen at the same time. So how do we find the probability of 2 events if they are not disjoint? So in this case now, the probability of A or B, if A and B are not disjoint, is equal to the probability that A occurs plus the probability that B occurs minus the probability that A and B occur at the same time. So there's the formula. So let's go ahead and take a look at this. Again, we are using a deck of cards as our example. So keep that photo of the cards up if you pulled that up. So I want to find the probability of drawing a king or a diamond from a deck of cards. These are not disjoint events because it is possible for me to draw one card and have it be a king and a diamond at the same time. So for this one, I'm looking for the probability of a king or a diamond. To save space, I'm drawing the diamond. So following this formula that I have up here, I don't have room to write out quite as much as I'd like. But king or a diamond, so the probability that I get a king, we found before, is 4 over 52 total cards, plus how many cards in the deck are diamonds. So it's ace through king. There are 13 diamonds out of the 52 total cards. And then we want to subtract how many cards are a king and a diamond. So there's only one card that is a king and a diamond. Okay, so 4 plus 13 is 17, minus 1 is 16 over 52, which gives us 0.3077. Again, make sure you're giving me 4 decimals with all this probability stuff. All right, another example. Now we want to find the probability that we draw an even numbered card or the probability that we draw a red card. So now I want the probability of an even or a red. So first I need to find the probability of an even card. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20. A queen is not an even card. A queen is a face card. So there are 20 even numbered cards out of the 52 cards total. Plus, how many cards in a deck of cards are red? There are 26 red cards, half of the deck. And then we want to subtract, not add, subtract the number of cards that are even and red, which is 10 out of 52. So 20 plus 26 is 46, minus 10 is 36 out of 52. which is 0.6923. And there we go. So you look at the probability of the first event by itself, add the probability of the second event by itself, and then subtract the probability that the two events happen at the same time. If you struggled with this on how to kind of visualize it, what I recommend doing is creating Venn diagrams. So create an image of two circles that overlap. Start by writing what's inside the two. So what are the two things that they have in common? So for example, we would have like the king of diamonds. Okay, and then over here you would have the other kings and then all of the diamonds. And that can help you visualize what you're going to be doing with this. Okay. All right, so the next thing we're going to talk about is the intersection of two events. So the intersection is the two events happening at the same time. And in order to find the intersection, we are only going to focus on events that are independent. So two events are independent if knowing the outcome of the first event does not provide any information about the outcome of the second event. So they're independent if knowing what happened for the first event doesn't give you any information about what's going to happen with the second event. So I have 3 examples here that we're going to determine if they're independent or dependent. The first one we're looking at is flipping a coin and rolling a die. So ask yourself, okay, if I flip a coin and I get a heads, is that going to tell me anything about what's going to happen when I roll the die? And the answer is no, it doesn't. Therefore, these two events are independent. Second one, we have the event that a person has a bachelor's degree, and the second event is that a person makes more than $100,000 a year. So again, ask yourself, does knowing a person have a bachelor's degree tell me anything about the probability that a person makes more than $100,000 a year? And the answer is yes. Typically, not always, but typically, the more education you have, the higher your probability is of making 6 figures or making over $100,000 a year. So in this case, having a bachelor's degree and being able to earn that much money are dependent events. And then finally, a driver in Chicago gets into an accident and a driver in Denver gets into an accident. So if you know that the driver in Chicago got into a car accident, does that tell you anything about the driver in Denver? And the answer is no. Therefore, they are independent events. So there's an example on looking at the difference between independent and dependent events. There is a way to calculate the intersection for dependent events, but we're just not going to cover that. All right, so now let's look at finding the probability that 2 events occur if those 2 events are independent of each other. So the probability that the event A and, keyword, the event B occur is going to be equal to the probability of A times the probability of B. So we'll look at an example. So you flip a coin 2 times, resulting in a heads and then a tails. So I want to find the probability that I get a heads and then I get a tails. So I'm looking for the probability of a heads and a tails. So if I flip a coin, the probability that I get a heads is equal to 1/2 times the probability that I get a tails is also equal to 1/2. 1/2 times 1/2 is 1/4, or 0.25. And yes, flipping a coin 2 different times are independent events. So now the second example I have here, I'm drawing 4 cards from a deck. I'm replacing the card after each draw. So I want to know the probability that I get a 2, a face card, a club, and finally a red card. So I'm going to be drawing 4 cards total. And after each draw, I replace it. So knowing that I got a 2 on the first draw, because I then put the card back and draw again, that doesn't give me any information about what is going to happen for the next draw. So these are still independent events. So here I'm looking for the probability of a 2, a face card, which is a jack, queen, or king, a club, and then a red. Okay, so the probability that I get a 2 is 4 over 52 times the probability of a face card. There are 12 face cards, meaning cards with faces on them, out of the 52 cards, times the probability of a club is 13 over 52. And then finally, the probability of a red card is 26 over 52. So a good reminder on how to multiply fractions. You multiply all of the top numbers together first. Then you multiply the denominators together. So I'm going to do 4 times 12 times 13 times 26, which gives me 16224. And that's going to be divided by 52 times itself 4 times, or 52 to the 4th power. So 52 times 52 times 52 times 52, which is 7311616. And then again, we want to turn this into a decimal. So 16224 divided by 7311616 gives me 0.0022. So the probability that I draw these 4 cards, a 2 followed by a face card, and then a club, and then a red card, is equal to 0.0022. Pretty small probability that I draw those 4 cards. Okay, so we're just multiplying the stuff together when they're independent events. So now let's look at another example. This one's a little bit harder. Okay, so you're taking a multiple choice exam that has 5 questions. Each question has 4 options, so it's A, B, C, or D. So find the probability that you guess each answer correctly. So you didn't even read the question, you just looked at the Scantron and you bubbled in A, B, C, or D without even reading the question. So you have no idea what the questions are about. So that means each one of them is going to be independent. So I want to know, what's the probability that you get them all correct? So come over here. So we want the probability that they're all correct. So each question is now independent of another because we're not even reading it. We don't know if one question relies on the other. The test is sitting on the floor next to us. We're just honestly just looking at our Scantron. Okay, so what is the probability? Before I can find the probability to get them all correct, let's just look at the probability that I get one question correct. Well, I have 4 options. Only one of those 4 options is going to be the correct answer. So it's going to be 1 over 4. That's the probability that I get a single question correct. So now to get them all correct, that means I have to get all 5 correct. So to get all of them correct, that's 1/4 for the first question times 1/4, which is the probability that I get the second question correct, plus times the probability that I get the third correct, times the probability that the 4th question is correct, times the probability that the 5th question is correct. And I'm not going to do that. That is not what I meant to do. What I meant to do was move this guy down. Let me just erase it real quick. and move it down a little bit further. Ooh, I'm sorry, y'all. There we go. So the probability that we get one question correct was 1/4. And then that's how we answered the rest of this. So now I'm going to come back up here. So I have, this is the first question, second question, third question, fourth question, fifth question. And each of these is the probability that I get that question correct. So now I'm going to go ahead and do that math. So 1 times 1 times 1 times 1 times 1 is 1. And then 4 times 4 times 4 times 4 times 4 is 1,024. 1 divided by 1,024. All right, here we go. So when you put this in your calculator, this is what you get. Okay, let me do this in a different color so you can see this. So in my calculator, I got this. 9.7, and then a bunch of numbers after that. And then I have this e to the negative 4. Okay, so when I look at this and I see 9.7, well, that can't be right because 9 is bigger than 1, and a probability can't be bigger than 1. So now I have this e to the negative 4 here. What that means is I need to take the decimal point and I need to move it 4 places to the left. So the negative means you're going to move the decimal place to the left, and the 4 tells you how many places. And then we're going to fill in each of these little humps that I've created with zeros. So now this is 0.00097. So if I want to round this to 4 places, the 7 is going to round the 9 up. So you add 1 to it. So we get 0.0010. So our answer is 0.0010. So if you're taking a test that has 5 questions and there are 4 options for each question, and you guess on all 4 of them, the probability that you get 100% on that exam is 0.0010, or about 0.1%. Not very good chances. Okay, read your test questions. That's basically what this problem is telling us, right? We got to read the questions. We can't just blindly guess. Okay. All right. So now, let's keep scrolling down. So this is the last thing we're going to talk about in Module 9. This is a contingency table. So a contingency table is a table that shows us the values for a survey result with 2 questions. So we had a group of people and we asked them, are you male or female? Or we looked at whether they were male or female. And then we also asked them what their marital status is. And they told us whether they've never been married, they're married, widowed, divorced, or separated. Divorced and separated are different. They are not the same. Separated people are not legally divorced from each other. They may live in separate places, but legally they are still married. Okay? So there is a distinction between divorced and separated. So now we can use this table to answer questions with probabilities. So the first question we have in regards to this table says, find the probability that a randomly selected person is a widow. So to do this, I'm going to look at my row of widows. So I'm going to circle it. Okay, and I want to look at the total number of widows that I have, which is 14. And then I need to know how many people did I look at total, which is 249. So the probability, I'm going to erase some of these circles now though, because it's too many. So the probability that I randomly select a widow is 14 over 249. which again, always want to turn this stuff into decimals, 0.0562. Okay, so that's a basic one, just looking at widow. I could do the same thing with females. I could ask, what's the probability that you randomly select a female? So now let's look at a little more challenging of a question. So find the probability that a randomly selected person is a widow or divorced. So key word in this problem is or, which we saw earlier in these notes. When we see the word or, that means we want to do addition. So I'm looking for the probability of a widow or a divorced. Okay, in this table, you are either widowed or divorced. You can't be both. In real life, you could be both, but with this table, there was no option for both of them. Okay, someone had to say whether they were widowed or divorced. If they were both, don't know what happened. They weren't included. Okay. So widowed or divorced, so we want to find first the probability that someone is widowed, which we just found as 14 over 249, plus the probability that a person is divorced. So looking at my divorced row, I go all the way over to the total. There are 25 divorced people out of the 249 total. So 14 plus 25 divided by 249. So it's 39 over 249, which is 0.1566. All right, next example. Find the probability that a randomly selected person is a widow or male. So now notice, if I come into my table, I'm going to do this in a lighter color. Here is my widowed row. That didn't work. Right? So here are all my widowed people. And then I'm also looking at the males, which is this one. Notice how one of these is a horizontal column and one is a vertical. This means that these are events that are not disjoint. You can be a widow and a male at the same time, but the question is asking for or. So that means we're going to have to do some addition followed by some subtraction. So I'm going to go ahead and leave that circled in yellow. That's fine. So find the probability that a randomly selected person is a widow or a male. So probability of a widow or a male. So first, the probability of a widow is 14 out of 249. We've seen that quite a bit. Plus the probability of a male, there are 122 males total out of the 249 people. And now minus the probability that they both happen. So how many people are widowed and male? That's where we're going to look at the intersection where these two circles are overlapping. So there are 3 widowed males in this table or from this survey. So minus 3 out of 249. Notice all of these totals so far, or all of these denominators, are my totals. I'm not doing anything with different denominators. That'll come next. So 14 plus 122 minus 3 is 133. And then we want to divide that by 249. So I added up my numerators, divide by the denominator 249. That gives me 0.5341. All right. And then D, find the probability that a randomly selected person is a widow and a male. So we have the keyword and here, okay? But these are not independent events. If I know that I'm looking at a widow, that changes the probability that I'm looking at a male. So we're not going to do the multiplication that we did previously when we saw the word and. When you're looking at a contingency table, looking for a widow and a male means you're just looking for where do those two events intersect. So again, we're looking at the widows and the males, which I already have circled. So there are 3 widowed males out of my 249 total. So 3 out of 249, which is 0.120. 0.120. So even though we saw the word and previously we did multiplication with that, these are not independent events. Therefore, we are not going to do any multiplication. Contingency tables, you do not need to do any multiplication. You just look for where do those two events overlap. Okay. So there is a contingency table problem. And that finishes the Module 9 part of these notes. There's one more page in these notes, which is Module 10, but I want to recap everything we just did in Module 9 first. So we started by looking at the complement of events, followed by the union of two events that are disjoint, so looking at the probability of A or B. Then we looked at the union of two events that are not disjoint, so A or B, when the two events can occur at the same time. Then we looked at the intersection of two events, so we looked at where A and B occur. If they are independent, we only looked at independent events with this. And then finally, we looked at how to calculate probabilities using a contingency table. So now Module 10, we just do a little bit with Module 10. Module 10 looks at the probability of conditional events. So the probability of dependent events. So we know the probability of the first thing, and therefore that changes the probability of the second event. So we're only going to focus on conditional probabilities in terms of contingency tables. We're not going to be worried about independent events with these or anything like that. We're just going to look at how do you find a conditional probability if you have the information in a contingency table. So let's go ahead and look at the first question here. So this first one says, find the probability that a randomly selected person is widowed given that they are male. So there's a very important piece to this probability, or to this question, and it says given that they are male. So that means I know I'm only looking at men. So I have these 249 people in the room. And I said, okay, if you are male, please stand up. And 122 men stood up. Then I said, okay, stay standing if you are a widow. And so all but 3 of those men sat down. So the probability, I wanted that to stay yellow. The probability that I pick a widow given that they are male, which is going to be written as widow, a straight vertical line, which stands for given, they are male. It's going to be equal to the 3 men that stayed standing out of the 122 men that stood in the first place, which is 0.0246. So first you look at the given piece and you say, okay, how many do I have that are male? And then out of those 122 males, how many of those are widowed? So as soon as I saw given they are male, I don't care about any of the females. I only care about the males right now. Okay, I hope that makes sense. I really wanted to just ask, does that make sense? And then realized you can't respond to that question right away. Okay. So now find the probability that a randomly selected person is male given that they are widowed. So again, I have this given statement, given that they are widowed. So now in my brain I say, okay, I only care about the people that are widowed. So I only care about this row. I don't care about people that have been never married or divorced or separated. I don't care about them. The only people I care about right now are the people that are widows. And of those people, I want to know how many of them are males. So I have 249 people sitting in a room in front of me. I say, please stand up if you are a widow. 14 people stand up. Then I say, stay standing if you are male. 11 females sit down, so I'm left with 3 standing males. So now the probability that I have a male given that they are a widow is equal to 3 over 14. So 14 is the total number of widowed people, and 3 is the number of males that are widowed, which is 0.2143. Okay. All right, and the last question, this is just another way to word this. Find the probability that a randomly selected person is a married woman. Okay. So this one, I'm looking at the probability that someone is married given that she's a woman. Actually, I don't think I worded this question correctly. This is not actually a given question. I apologize. This is just a simple intersection problem. That's okay. It's good practice. I thought I had written this in a different form, but I didn't. So now I want to know the probability that I have a married woman. So I need to find how many married women I have total. So married women, there are 63 out of the 249. So 63 out of 249. Again, I apologize. I thought I had written this question differently, but upon reading it again, discovered I didn't. 0.2530. Okay, but the big thing with conditional probability that we're focusing on for this course is this given aspect and looking at, okay, how can we find that answer by looking at a contingency table? So whatever is given, the total for that given quality becomes your denominator in your fraction. So we said given they are male, so I looked at the males and I said, okay, there are 122. So out of the 122 males total, how many of them were widowed? And then I did the same thing with the second one. Given they are widowed, okay, there are 14 widows. Out of those 14 widows, how many of them are male? So that is all we're going to focus on with conditional probability. Okay, and that concludes modules 9 and 10.